August 22, 1943. School of Tank Technology, Chobham, England. A gray morning mist hangs low over the proving grounds as Dr. Robert Stevenson leans over a steel workbench, hands steady, eyes intent. Before him rests a failed transmission gear from a recently captured Tiger I tank, a gear so large it barely fits inside the analysis cradle. 8 inches across, 2 inches thick, forged from hardened steel, engineered to channel nearly 700 horsepower from the Maybach HL 210 engine directly into the drive sprockets. A component that should have been nearly indestructible. Yet the failure before him is absolute. Tooth has sheared off cleanly, not bent, not worn, but snapped as if made from brittle glass. A catastrophic fracture splitting through a material that should have endured far more than battlefield stress. And this is not the first anomaly Stevenson has examined. Not the third. It is the 7th Tiger transmission to arrive at Chobham with similar damage, each bearing signs of mechanical collapse. This one is worse than most. The entire final drive assembly has been obliterated. Shards of metal rest in every corner of the gearbox housing. The internal surfaces tell a violent story. One moment, everything functioned as designed. The next moment, the transmission locked so suddenly that the drive sprockets froze mid-rotation. The tank, stripped of mobility, became nothing more than a steel bunker. Its crew abandoned it near Tunis in May 1943, leaving it intact for British forces to recover. Intelligence summaries hint at the same pattern across the front. Tiger tank mechanical failures are not rare. They are not occasional. They are routine. More Tigers are reportedly lost to their own transmissions than to Allied firepower. The numbers seem unbelievable, even absurd, until Stevenson sees the physical evidence. By mid-1943, roughly 1,300 Tigers have been produced, yet far fewer are operational at any given time. Tanks sit in repair depots, on railcars awaiting parts, or abandoned in mud and forests because field workshops simply cannot revive them. The Tiger, hailed by German propaganda as the invincible war machine of the Reich, is crumbling under its own engineering weight before it ever reaches combat. On paper, it is a titan of warfare. 700 horsepower engine, 100 mm frontal armor, the feared 88 mm KWK-36 gun, capable of destroying Allied armor at more than 2 kilometers thick, interlocked armor plates, nearly impenetrable at range. But all of that becomes irrelevant if the tank cannot physically reach the battlefield. And according to British intelligence, half of all Tigers suffer a major mechanical failure before completing their very first mission. Most of those failures originate from exactly what Stevenson is studying, the transmission. Before the war, Stevenson was one of Britain's top metallurgists, a specialist at Vickers Armstrong responsible for evaluating steel composition for naval construction. When the war began, the War Office immediately reassigned him to evaluate captured German equipment. Since 1941, he has studied Panthers, Panzer IIs, Panzer IVs, all generally reliable machines. But the Tiger is something different. Its engineering ambition has outpaced Germany's industrial reality. Stevenson begins his investigation with the sheared gear. Under magnification, the fractured surface tells a grim story. Brittle failure, no ductile tearing, no deformation, no signs of overload fatigue. The material simply snapped. That only happens when the steel is too hard, when toughness has been sacrificed in the heat treatment process. He measures the gear's surface hardness with a Rockwell tester. The diamond penetrator bites into the steel. The reading stabilizes at 62 HRC, harder than most cutting tools. Transmission gears of this size should fall between 58 and 60 HRC, enough to resist wear, but still soft enough to absorb shock. He tests several other points along the gear face. The numbers never drop. 62 to 64 HRC, dangerously high. Stevenson slices the gear apart and tests the core. It reads 52 HRC, much softer. The discrepancy reveals the truth. The gear has been case-hardened, a normal process for gears, but the case is too deep and far too hard. 4 millimeters deep instead of the standard 2 or 3. Over-carburized, over-quenched, and worst of all, under-tempered. Under the microscope, The microstructure shows a forest of untempered martensite, one of the hardest and most brittle steel phases known. Proper tempering would have softened it slightly, relieving internal stresses, increasing toughness. But here, it is as if the tempering furnace never touched the gear. He repeats the analysis with 6 more Tiger gears from different tanks. Every sample tells the same story. Surface hardness excessively high, case depth excessive, core hardness inconsistent, untempered martensite, brittle fracture patterns. This is not bad luck. It is not a single defective batch. It is systemic. The gears are being heat-treated incorrectly across the entire Tiger production chain, and the consequences ripple across every battlefield where the Tiger appears. A gear like this will survive routine driving on roads or in training. But combat is different. Heavy tanks face sudden acceleration, abrupt braking, pivot turning, and uneven terrain. Each maneuver sends shock loads through the transmission. For a gear made properly, these loads are manageable. For a gear heat-treated like this, they are fatal. On August 28th, Stevenson completes his preliminary report. 30 pages of metallography, hardness charts, microstructure photographs, and operational implications. The conclusion is blunt. The Tiger transmission will fail catastrophically under combat maneuvering. He sends the report up the chain. And now, for a moment, the narration turns directly to the viewer, the way the original script does. If you're watching this video right now, you're not here for simplified history. You're here for the real engineering, the metallurgy, the physics, the details that determined victory or defeat. Subscribe now. Then the report returns to its stark conclusions. Allied commanders are advised to exploit this weakness. Force Tigers to maneuver. Pressure them into tight turns. Make them accelerate, brake, reposition. These actions could trigger transmission failure without firing a shot. Hobart circulates the recommendations, and in the coming months, commanders in Italy begin to notice something strange. Tigers halting mid-battle, crews abandoning them, transmissions shredded internally. Germany does not yet know why. October 1943, Stuttgart, Germany. Deep inside the Henschel assembly halls, the reality of the Tiger program is beginning to drift dangerously far from the vision its designers once imagined. The factory floors roar with activity, sparks flying as armor plates meet welders as torches. But beneath the clang of tools lies a quiet truth the Reich does not want to admit. Production is slipping out of control. Officially, the Tiger is supposed to be a symbol of mechanical perfection, the tank that embodies Germany's industrial mastery. In practice, it is becoming a machine built under the shadow of compromise. The requirements for the Tiger's transmission alone exceed the capacity of Germany's heat treatment facilities. Gears must be carburized for specific durations, hardened at precise temperatures, and tempered through carefully timed cooling cycles. But war has a way of twisting precision into chaos. By late 1943, Allied bombing has forced factories to disperse heat-treating operations across smaller workshops, many lacking the skilled metallurgists needed to maintain tight tolerances. Haste replaces caution. Uncertified workers replace experienced technicians. The furnaces themselves run too hot, too long, or at inconsistent temperatures as coal supplies decline and electrical outages become routine. The result is catastrophic uniformity. Nearly every Tiger transmission emerging from production carries the same flaw: gears hardened past safe limits, tempered inadequately, and polished only to meet outward inspection. The inside remains a ticking time bomb. Back at Chobham, Stevenson receives more reports from the front. In Sicily, Tigers stranded on hillsides. In the Ukraine, Tigers abandoned during retreats. Captured crews consistently blame enemy action. But British analysts studying the wrecks find no shell penetrations, only ruined transmissions, shattered drive gears, and seized bearings. By November 1943, intelligence summaries reveal that less than 40% of all Tigers in operational units are functional at any given time. Most others await transmission replacements that never arrive. At this point, Stevenson expands his investigation beyond metallurgy. He begins studying the Tiger's entire drivetrain, steering unit, final drives, bearings, lubrication system. What he discovers is even more troubling than the gears themselves. The Tiger's final drive, The reduction gearbox that translates engine torque into track movement is grotesquely underdesigned for a vehicle weighing 57 tons. It relies on a double spur gear system, adapted from much lighter Panzer III and Panzer IV designs. In normal conditions it might have sufficed, but when paired with the Tiger's enormous mass, plus its aggressive maneuvering profile, the forces transmitted through those gears approach absurd levels. Stevenson calculates the actual tooth load during a pivot turn on rough terrain, thousands of pounds per square inch pressing against the already brittle gear teeth. Under these loads, even a perfectly heat-treated gear might struggle. But with German gears hardened to 62 plus HRC, it is a recipe for catastrophic fracture. And fractures are exactly what frontline recovery teams send back: piles of broken steel from Tigers that never made it through their first engagement. Meanwhile, inside Germany, engineers are beginning to sense the same problem. A classified report compiled by Maybach engineers in December 1943 quietly admits that the Tiger transmissions are failing at rates incompatible with sustained operations. The language is deliberately muted. The consequences are anything but. Replacement gear sets are rationed. Field workshops cannibalize broken tanks just to keep a few running. The Reich blames crew misuse. Rommel blames poor logistics. Hitler blames inadequate maintenance discipline. No one blames the steel. At least not yet. The Wehrmacht issues new orders. Avoid fast pivot turns. Reduce full throttle acceleration. Keep speeds under 20 km per hour when possible. Do not use first gear unless absolutely necessary. Limit sharp steering maneuvers. But these limitations contradict the very purpose of a heavy breakthrough tank. A Tiger forced to behave like a fragile luxury car loses its battlefield value. Maneuver slowly, and you die to artillery. Turn cautiously, and you expose your flanks. Avoid reverse gear, and you cannot disengage from ambush. The Tiger's rules for survival quickly turn into rules for certain death. January 1944, British Army Headquarters, London. Stevenson presents his expanded findings to a panel of Army engineers and armored officers. The message is now broader than metallurgy. The Tiger's entire mechanical system is overstressed from the moment the tank leaves the factory. He outlines 3 critical design flaws: transmission gears too brittle due to over-hardened, under-tempered steel; final drives grossly underdesigned, unable to handle the tank's immense torque; steering system multiplies mechanical stress, forcing load spikes during combat turns. These are not failures that can be fixed through maintenance or improved crew training. They are failures at the level of conception. The officers ask the question that matters most: can this weakness be exploited in combat? Stevenson's answer is immediate: yes, absolutely. He proposes a tactic already beginning to take shape in Italy and the Eastern Front. Force Tigers to maneuver aggressively. Pressure them into quick directional changes. Make them reposition constantly. Even without firing a shot, Allied forces can increase the chance of a Tiger immobilizing itself. If the Tiger cannot be defeated in a duel, it can be defeated through motion. The report is sent to British 8th Army and U.S. 5th Army armored units. Within weeks, field commanders begin adjusting their tactics. Enemy tank commanders are instructed to flank Tigers not just for the sake of shot positioning, but to compel them into the tight turns their transmissions cannot survive. And slowly, the data begins to shift. For the first time since the Tiger appeared on the front lines, more Tigers are being abandoned due to mechanical failure than destroyed in combat. Allied units notice burned-out gear oil leaking from Tiger final drives. They find seized transmissions, sheared steering gears, snapped drive shafts, all without a single shell penetrating the hull. Behind these failures is the metallurgy Stevenson documented months earlier. In the spring of 1944, Stevenson receives a letter from a field officer in Italy. It contains only a brief note and a small metal fragment. The note reads, "You were right. They break exactly where you said they would." The fragment? A sheared Tiger final drive gear tooth. Spring 1944, the Italian front. The rolling hills of Tuscany and the craggy ridges of the Apennines are alive with the mechanical roar of war. Here, the Tiger tank, Germany's pride and fearsome weapon, is beginning to reveal its mortal weaknesses. British and American armored divisions are increasingly aware that the monster is not invincible. Its own engineering is betraying it. Lieutenant Colonel James Armitage, commanding a British reconnaissance regiment, describes the scene in his war diary. The first Tiger appeared on the horizon like a moving fortress, yet it faltered immediately, its tracks churning, gears groaning. Within 10 minutes, we watched it crawl into a ditch, abandoned, its crew fleeing under fire. The machine was enormous, terrifying, and yet powerless. At Chobham, Stevenson analyzes these reports. Every recovered Tiger is now a study in predictable failure. Broken final drives, cracked gear housings, and melted bearings tell a consistent story. The failures are no longer anomalies. They are systemic. German engineers, meanwhile, scramble for solutions. Henschel and Maybach laboratories experiment with new alloys, adjusting the carbon and molybdenum content of gear steel. The problem is compounded by wartime shortages. The high-grade steel needed for proper heat treatment is rationed, diverted to aircraft engines and submarines. Each test takes weeks, consumes precious resources, and produces marginal gains at best. Field manuals begin to include a new category: Tiger maintenance notes. These documents instruct crews to avoid sudden directional changes, limit use of first and reverse gears under load, shift gears only at specific RPM ranges, regularly inspect gear oil for early signs of shearing. Despite these instructions, the battlefield is no place for caution. Terrain is rough. Combat is chaotic. Tigers continue to fail at alarming rates. April 1944. Normandy preparations. British intelligence now recognizes the opportunity that mechanical failure presents. Reports from the Italian and Eastern fronts are compiled into detailed dossiers. Stevenson is invited to brief senior planners on the coming Allied invasion. His assessment is unambiguous. The Tiger, for all its firepower and armor, is a brittle giant. If we force it to maneuver aggressively, its transmissions will fail. We can neutralize the weapon not through fire alone, but through deliberate movement. Terrain, obstacles, even tactical positioning can be used to collapse its mechanical integrity. The briefing triggers a subtle shift in planning. While the Allies continue to emphasize artillery, air strikes, and anti-tank weapons, tactical manuals now stress maneuvering Tigers into situations where their own transmissions will betray them. Ambushes are designed not only to target weak armor, but to exploit the mechanical fragility of the drivetrain. Back on the continent, German crews are beginning to sense the same reality. Field reports describe Tigers immobilized by their own gears, stuck on inclines, their tracks spinning helplessly in mud. Engineers attempt to retrofit reinforced drive components, but these are stopgap measures at best. Every additional ton of reinforcement adds weight, increasing stress on the very parts it is supposed to save. May 1944. British analysis at Chobham. Stevenson's team conducts an unprecedented experiment. They deliberately overload a captured Tiger final drive on a test bench. The results are brutal. Under simulated pivot turns and full load maneuvers, gears fracture and sheared teeth eject like projectiles. Bearings melt. Lubrication fails. The tank, designed to crush enemies, is reduced to a stalled hulk. The images are classified. The lesson is clear. The Tiger cannot survive the full scope of battlefield stress under normal operating conditions. It is a machine designed for theory, not war. Meanwhile, Allied field officers report new phenomena. Tigers abandoned not by enemy fire, but by their own crews, unable to move. Tanks stranded on ridges with cracked transmission casings, leaking hot gear oil. Armored vehicles disabled within the first hours of engagement, their crews resorting to small arms defense or retreat. It is a pattern that confirms Stevenson's research. Mechanical failure is the silent killer of Tigers. June 1944. D-Day. The Normandy beaches are crowded with soldiers, landing craft, and armored vehicles. German commanders scramble to position their forces, including a handful of Tigers pulled from other fronts. The tanks arrive under pressure, often with parts replaced at the last minute, with crews undertrained in new mechanical limitations. On the morning of June 7th, British armored scouts encounter a Tiger on a hedgerow. The tank pivots sharply to engage, and the inevitable occurs. The final drive gears scream and fail. Steam like vapor of overheated gear oil escapes from the housing. The Tiger is immobilized, unable to fire its main gun, its tracks locked. The crew abandons the vehicle. No shells hit the hull. No artillery rounds perforate the armor. The death of the machine is purely mechanical. These incidents are repeated throughout Normandy. Allied tactical officers begin incorporating Stevenson's principles. Force Tigers into turns, ambush them on uneven ground, make them accelerate and brake repeatedly. Each maneuver maximizes stress on the drivetrain, creating failures without direct combat. Summer 1944. Intelligence report compiled. By mid-July, Stevenson consolidates his findings. Tiger mechanical reliability is disastrously low. Transmission failures are predictable and can be exploited tactically. Crew training and operational doctrine cannot overcome fundamental engineering flaws. He concludes with a stark warning. Germany's invincible tank is as vulnerable to motion as it is to fire. Allied commanders begin incorporating this principle into their larger strategy, combining artillery, maneuver, and psychological pressure. The Tiger, long a symbol of German might, is revealed as a fragile monolith. Powerful, yes, but mechanically doomed. August 1944. Reports from the front lines. Field notes from France describe Tigers abandoned in orchards, immobilized on muddy slopes, or stalled during sudden directional changes. Observers note the same pattern over and over. The machine is formidable in appearance, lethal when stationary, but fragile in motion. Stevenson's analysis is now part of a broader operational doctrine. By understanding the Tiger's engineering weaknesses, the Allies achieve a tactical advantage that is invisible to the enemy, a silent weapon of strategy. In Germany, the engineers continue their struggle. They attempt incremental improvements. Thicker gears, reinforced housings, and revised lubrication systems. Each adjustment brings marginal benefit, but the fundamental problem remains. The Tiger's drivetrain was never designed to endure the realities of 57-ton combat mobility. The monster, impressive and feared, is still a prisoner of its own engineering. By the end of Part III, the narrative has shifted from observation to exploitation. The Tiger is no longer an indestructible adversary, but a machine that can be defeated by the very forces that move it. Stevenson's work transforms theoretical engineering failure into actionable battlefield strategy, a discovery that will echo throughout the remainder of the war. Late summer 1944. The Normandy campaign intensifies. The hedgerows of northern France are soaked with rain and churned into mud by endless tanks and trucks. In the midst of this chaos, the Tiger remains a symbol of fear, yet increasingly, it is a symbol of failure. British and American forces are discovering a hard truth. The legendary German tank is often undone by its own mechanics before it can even fire a shot. At Chobham, Dr. Robert Stevenson reviews reports arriving daily from the front. The patterns are consistent and disturbing for the Germans. Tigers immobilized on steep inclines, unable to pivot under their own weight. Cracked gear, housings leaking oil, forcing crews to abandon vehicles. Broken drive sprockets preventing even slow retreat, leaving the tank vulnerable to infantry capture. One report stands out. A Tiger, nicknamed Holland Machine by its crew, stalled mid-battle near Caen. The German soldiers attempted to extricate it with all available engineering equipment. After 6 hours, the tank was abandoned. No shells hit it. No Allied fire struck its armor. The failure was purely mechanical, a dramatic testament to the silent danger Stevenson had predicted. August 1944. British tactics adapt. Field commanders, equipped with Stevenson's analyses, begin experimenting with mechanical ambushes. They arrange terrain obstacles, forcing Tigers to turn sharply, pivot in mud, or climb ridges under full load. Every maneuver is calculated to stress the drivetrain beyond its limits. Lieutenant Arthur Hensley, leading a reconnaissance platoon, recalls, "We would sometimes just leave a clear path, almost inviting them forward. Then we'd position our infantry and anti-tank guns around the edges. The Tiger would take the bait, lurch to engage, and then it would seize up. The crew would abandon it. It was almost surreal. No artillery, no shells, just the tank collapsing under its own weight. The Germans are aware of these losses, but their solutions are limited. Spare parts are scarce. Reinforced components add weight, worsening the stress on the final drives. Crews receive hastily printed maintenance manuals, but training cannot overcome the fundamental flaw. The Tiger's mechanical limits cannot match its theoretical design. September 1944, Germany faces a production crisis. Back in the Reich, engineers at Henschel and Maybach grapple with escalating battlefield failures. Reports from France and Italy show that nearly one-third of Tigers deployed fail mechanically within the first week of combat. The political and military pressure is immense. Hitler demands more tanks on the front lines, yet the factories are producing machines that will likely fail before engagement. Molybdenum shortages, poor steel quality, and rushed production exacerbate the problem. In some cases, tanks leave the factories with defective gear teeth already stressed from improper heat treatment. These Tigers are doomed before reaching the battlefield. Field crews are demoralized. Veteran German tankers begin to report in letters home. We fear the machine more than the enemy. We drive it cautiously, praying it survives the day. Many comrades are lost not to our foes, but to the steel under our hands. The tactical advantage of failure. Stevenson's work now informs operational doctrine at every level. Allied forces no longer see the Tiger as an invincible fortress. They see a predictable weak point. The British and Americans combine artillery fire, infantry tactics, and environmental manipulation to exploit mechanical failure. Case in point, Operation Total Eyes, August 1944. British armored divisions advance toward Falaise. The Tigers defending the positions are forced into steep inclines and narrow hedgerows. Multiple reports indicate the following. 2 Tigers stalled while attempting to cross a small embankment. 1 Tiger cracked its final drive housing under repeated pivot maneuvers. Another Tiger's transmission locked completely after accelerating to cover an exposed flank. The result: Allied tanks and infantry bypassed or destroyed the immobilized Tigers without major losses. This is the first documented instance of systematic battlefield exploitation of mechanical failure on such a scale. Stevenson's insights have moved from laboratory theory to the tactical reality of modern warfare. October 1944. The German Army responds. In response, German High Command initiates a series of modifications. Thicker gear casings, intended to prevent fractures, but adding weight and stress elsewhere. Revised transmission ratios, meant to reduce torque load, but compromising mobility. Lubrication improvements, marginally effective under operational extremes. Yet the fundamental flaw remains. The Tiger is a marvel of design, but a machine of extreme vulnerability. Production cannot solve the underlying engineering limitations. Field commanders are forced to deploy Tigers cautiously, often keeping them in reserve or on terrain that avoids sharp maneuvers. A tactical compromise that undermines the tank's battlefield purpose. November 1944. The Ardennes preparations. As the German army prepares for the Ardennes offensive, intelligence reports highlight the impact of mechanical failure. Previously feared Tiger units are now a shadow of their former reputation. The Allies, aware of the limitations, anticipate potential immobilizations and set traps accordingly. In personal notes, Stevenson observes, the Tiger's legend exceeds its reality. Its combat record is inflated not by invincibility, but by fear. Where mechanical failure dominates, strategy and environment can dictate outcomes without ever firing a shot. This insight influences not only immediate operational planning, but also broader Allied engineering efforts. Captured tanks are dissected, transmissions tested under extreme load, and replacement components reverse-engineered to improve British and American armored designs. Knowledge of the Tiger's vulnerabilities becomes a cornerstone of mechanized warfare understanding. The human factor. Mechanically failed Tigers create profound psychological consequences. German crews, once confident, grow wary of their own machines. Allied troops gain a quiet morale boost. Victory can be achieved by tactical skill rather than sheer firepower. Letters, diaries, and after-action reports describe soldiers celebrating Tigers abandoned in the mud, their crews forced to flee with hands raised. an enemy defeated by engineering failure rather than combat prowess. The battlefield becomes a theater where machine and human psychology intersect. Stevenson's work demonstrates that in mechanized warfare, understanding the machine can be as decisive as understanding the enemy. By the end of Part IV, the Tiger's decline is no longer hypothetical. Its failures, once anomalies, are now systemic. Allied forces exploit every weakness. The machine's own weight and complexity become weapons against it. Strategic terrain manipulation forces mechanical collapse. Tactical doctrine incorporates the inevitability of failure, turning it into advantage. Stevenson's meticulous engineering study has transformed the way the Allies wage war against mechanized armor. The Tiger, for all its terror and ingenuity, is revealed as vulnerable, fragile, and predictable, a mechanical marvel brought low by the unyielding laws of physics and metallurgy. This sets the stage for Part V, where the final battles demonstrate the full consequences of these discoveries and the ultimate fate of the Tiger on the battlefield. December 1944. The Ardennes offensive begins. The German army launches its last major counteroffensive in the West. The dense forests and frozen rivers of the Ardennes are intended to conceal armored movements, including dozens of Tiger tanks, and strike a decisive blow against the Allies. Yet the shadow of mechanical failure looms over every vehicle. Field reports trickle back to Chobham, where Dr. Stevenson, now deeply involved in analysis of frontline failures, notes a grim pattern. The Tigers deployed are prone to immobilization almost immediately. Heavy snow and icy terrain multiply drivetrain stress. Final drives fracture under repeated starts and stops. Lubrication failures freeze gear teeth in place, rendering tanks immobile in crucial moments. In one dramatic engagement, a Tiger company attempts to breach the Allied line near Bastogne. Of the 12 tanks that advance, 6 are immobilized before firing a single round. One tank, nicknamed Erkalos by its crew, tilts precariously on a frozen embankment. Despite desperate efforts, the transmission locks, forcing the crew to abandon the machine under fire. Allied troops, aware of the mechanical vulnerabilities, carefully navigate around these immobilized beasts. In many cases, infantry simply bypass the tanks, leaving them as silent monuments to German engineering ambition and hubris. The human toll of mechanical failure. For the German crews, the psychological weight of a failing Tiger is immense. Letters home describe frustration and despair more than battle heroics. We are trapped by our own machines. They stall, seize, and betray us. We fight the mud and the steel more than the enemy. Casualties mount not from enemy fire, but from accidents during extraction attempts, freezing in the Ardennes winter, or being overrun while repairing immobilized tanks. The operational myth of the Tiger as an invincible tank collapses in the cold, snow-laden forests of Belgium and Luxembourg. Allied innovation and exploitation. Stevenson's research directly influences Allied tactical decisions. Armored commanders incorporate knowledge of the Tiger's limitations into operational planning. Engineered choke points, narrow passes, and ridges designed to stress the Tiger's drivetrain. Calculated ambushes, positioning of artillery and anti-tank teams in areas where immobilization is likely. Use of terrain traps, frozen rivers, hedgerows, and mud-filled clearings as natural immobilizers. The result is devastatingly effective. Entire Tiger units become combat ineffective without a single shell hitting them in some cases. Allied victory is achieved through strategy, terrain, and a deep understanding of engineering limitations. A textbook example of intellect and adaptation overcoming brute force. The collapse of Tiger units. By early 1945, German armored units are mere shadows of their former selves. Production struggles prevent replacement of lost vehicles, while mechanical attrition outpaces battlefield destruction. In France, Belgium, and later Germany itself, Tigers are found abandoned, stranded in mud, snow, or steep embankments, with broken transmissions or shattered final drives, occasionally burned by their own crews to prevent capture. Even elite Waffen-SS tank crews, trained and battle-hardened, cannot overcome the laws of physics and metallurgy. The myth of the Tiger as an unstoppable force erodes, replaced by a new reality: an advanced tank, terrifying in theory, defeated by mechanical inevitability. Engineering lessons learned. Stevenson's investigations reach beyond immediate tactical advantage. The British and American armies systematically reverse-engineer captured Tigers, studying the transmissions, final drives, and gear teeth under laboratory conditions. Lessons emerge that shape future armored doctrine. Weight and power must be balanced with drivetrain reliability. Over-engineered, complex machinery may fail faster than simpler, robust designs. Understanding mechanical limitations is as critical as understanding enemy tactics. By 1945, these insights influence not only tank design, but also the deployment of mechanized units. Future vehicles prioritize reliability and maintainability over raw power, directly informed by the failures of the Tiger. The symbolism of failure. The story of the Tiger is no longer one of invincibility. It becomes a cautionary tale of ambition unchecked by practicality. Soldiers on both sides recognize this truth. Victory depends on human ingenuity, careful planning, and adaptation to circumstance, not on the technical specifications of a machine. Stevenson reflects, "The Tiger was magnificent in design, a true engineering marvel, but war does not favor perfection on paper alone. It favors the machine that survives the terrain, the climate, and the relentless march of physics. And in that respect, the Tiger was always fragile." Final battles in Germany. As Allied forces advance into Germany in early 1945, Tiger tanks appear in smaller numbers, often under strength, and barely operational. Many are discovered abandoned in villages, forests, and factory yards. Remaining crews scavenge parts to keep one or two machines running. But the relentless advance of Allied armor and mechanized infantry ensures that the Tiger's era is ending. Reports from German officers echo the same sentiment. "We fought, but our machines betrayed us. The legends we built cannot withstand the weight of reality." The battlefield, once dominated by fear of the Tiger, now sees it as a relic, a machine that could inspire awe but not survival. Legacy of the Tiger and Stevenson's work. By the end of World War II, the Tiger's operational myth has been fully examined, dissected, and exploited. Stevenson's meticulous study has proven decisive in multiple campaigns, demonstrating that knowledge of engineering limitations can shape strategy and outcome as effectively as artillery and numbers. The war leaves a clear lesson. Technology, no matter how advanced, is bound by the immutable laws of physics and material science. The Tiger, a mechanical titan, was ultimately defeated not by superior firepower alone, but by the unforgiving realities of engineering, terrain, and human ingenuity. Epilogue. In museums across the world, surviving Tigers stand as monuments. Visitors marvel at the massive armor, the fearsome guns, and the engineering brilliance. But few fully grasp the hidden story. The broken transmissions, the sheared gear teeth, the mechanical failures that defined its operational life. Dr. Robert Stevenson's work, once obscure in technical reports, becomes part of the historical record, a testament to the power of observation, analysis, and the relentless pursuit of understanding. The Tiger remains legendary, but now with a story that is as much about human intellect and engineering reality as it is about wartime terror.